This is a brief overview of solvation, which is the process by which solutes become dissolved in solvents. What exactly does it mean for a substance to become solvated? Well, if you look at a solute and it has a certain type of intermolecular attraction between the solute molecules, and in order for a solute to dissolve in water, the intermolecular forces between the solute and the solvent, here, in this case the solvent's water, so the attraction between the solvent and the solute have to be stronger than the attractions between solute molecules. Otherwise the solute will not dissolve. And so solvation is when you take an individual solute molecule and you surround it by water molecules. And the reason that happens is because the water molecules and the solute molecules are attracted to each other. They have intermolecular forces. So solubility depends on the strength of the intermolecular force between the solute and the solvent. All right, so both ionic compounds and covalent compounds get solvated and can possibly dissolve in water, but the process by which they do that looks a little different if you draw molecular models. So I'm going to draw an example of each. And so for ionic compounds dissolving in water, I'm going to use sodium chloride as the model. And sodium chloride in the solid state, in the dry state, looks something like this. So you have a bunch of NaCl units all attracted to each other because opposite charges attract. And you end up with kind of a three-dimensional network of sodium chloride units. And then when you put it in water, what happens is the attraction between the individual ions, the sodium ions and the chloride ions, are very attracted to the water molecules. And so you can kind of think of solvation of an ionic compound as pulling the ions away from the other ions they're attracted to. So let's now draw solvation of the individual ions in sodium chloride. Sodium ion, of course, has a positive charge, so it is going to be attracted to the negative end of water. And although water does not have a full negative charge, it is a polar molecule, and it has partial negative and partial positive charges. That's simply because oxygen is more electronegative than hydrogen, and therefore is going to hog the electrons, end up with a partial negative charge. So the sodium with its positive charge is going to be attracted to the negative end, or the oxygen end, of water. So the water molecules that solvate the sodium ions are going to orient themselves so that the oxygen atom is closest to the sodium ion. Okay? So the solvent cage, or the solvation, is going to look kind of like that. And likewise, the chloride ion, which has a negative charge, I've run out of room now, is going to be attracted to the positive end of the water molecules, which is the hydrogen atoms. So when you show the solvation of an anion, you want to orient the hydrogen atoms of the water molecules closest to the negatively charged ion. So you should be able to draw both of these molecular model representations. This diagram shows better representation than I do with my chicken scratchings, so it might make more sense to you. The sodium chloride in the solid form, undissociated, looks kind of like this, and the smaller ones would be the cation, the sodium ions, and the larger ones would be the chloride anions. And so when sodium chloride or a soluble ionic compound is put in water, the individual ions begin to get pulled away from this three-dimensional attractive mess and solvated by water molecules. Notice again the anion is surrounded or solvated by water molecules with the hydrogen atoms oriented towards the negatively charged anion. And the hydrogen ion, no, not hydrogen, the sodium ion, okay, with its positive charge, gets surrounded by water molecules that are oriented with their oxygen pointed toward the positive charge. So in summary, it's important to realize that all soluble ionic compounds dissociate when they are dissolved in water. Okay, all soluble ionic compounds dissociate. Sometimes that'll be called ionized when dissolved in water. And what do they dissociate into? They dissociate into the cation and anion. Okay, so you would show that process. Usually water is drawn over an arrow. You would show the process like this. Okay? So covalently bonded compounds can dissolve in water too. The overriding principle for whether or not something is going to be soluble is that polar substances dissolve in each other and nonpolar substances dissolve in each other. A polar substance solute will not dissolve in a nonpolar solvent and vice versa. Okay? So it's very important to be able to identify a solute and a solvent as polar or nonpolar. If you're not confident with that yet, you may want to listen to the other pre-recorded lecture I have on identifying polarity. All right, so what happens if a covalently bonded compound dissolves in water? Covalently bonded compounds do not dissociate. That's very, very important to realize. If the compound the solute you're talking about is made up completely of nonmetals, no metals in them, that means it's covalently bonded, and covalently bonded compounds do not dissociate, okay? They don't contain any ions. They stay intact. So how is it that they dissolve in water? Well, dissolving something always depends on the intermolecular forces between the solvent and the solute. And hopefully at this point you can see that the intermolecular force between this solute, which happens to be ethanol, and water molecules are very strong. They are hydrogen bonding because both the solvent and the solute have hydrogen atoms directly bonded to an oxygen. So they can both participate in hydrogen bonding, therefore the attraction between them is very strong, and ethanol does in fact dissolve in water. So covalently bonded compounds do in fact undergo solvation, they just don't dissociate. Okay, sugar, you certainly don't have to memorize the formula or the structure, but just to understand why sugar dissolves in water, sugar is another covalent compound. Okay, there are all nonmetals in the structure, no metals. And if you look at the structure of sugar, it's certainly polar because it's not made exclusively of carbon and hydrogen or all of the same element. And it has quite a few OHs, okay? That means that sugar can also participate in hydrogen bonding. So sugar is quite soluble in water also. Well, petroleum, that just means oil, okay? Oil, gas, all of those things are in the same family. They are all hydrocarbons. Hydrocarbon means a compound composed only of carbon and hydrogen. Hydrocarbons are nonpolar. The electronegativity of carbon and hydrogen are very, very similar, and so one of them doesn't hog the bonding electrons more than the other. And because it's nonpolar, hydrocarbons or petroleum-based materials do not dissolve in water because water is polar. They would dissolve in other hydrocarbon-based materials, other nonpolar materials. So of course that explains why salad dressing, for example, when you have both water and oil present, you get separation of layers. Okay, they don't like each other. Oil has London dispersion intermolecular forces. It is nonpolar. And water has hydrogen bonding, so they really are not attracted to each other. They don't have intermolecular attractions that are strong, and so they prefer to stay with their own type. So that's it for a summary of Solvation. What you need to know out of this for the upcoming test, you need to understand Solvation. You need to be able to draw models showing what Solvation is, and you need to be able to identify, if I give you a list of compounds, which ones might dissolve in water, a polar solvent, and which ones might dissolve in something that's hydrocarbon-based, a nonpolar solvent.